Okay, I'm going to try this. I told you I might try this. I'm going to try it. And if it's a failure, you probably will never even know. So hello, because it doesn't matter. But we did this problem in the previous video. I'll link it down below, where we have a shell with a permanent, frozen polarization, and we wanted to find the electric field everywhere. Could we do this numerically? Could we do this numerically and model this numerically? Yes, we can. So we need to do a couple things. Number one, I don't want to forget this electric field on the inside of the thing in the middle. It's negative k over epsilon naught r. And 0 and 0 in other places. But what I want to do is to instead build this into a region and put a whole bunch of dipole moments in there and then use that to calculate the electric field. So there's a couple things we need. Number one, how do you calculate the electric field due to a dipole? So if I have some dipole, P, a dipole moment, not the polarization, then I can find the electric field at some observation location R as 3 times P dot R hat minus P, all of that over 4 pi epsilon naught R cubed. That's how I could find that. But the thing is, we had this polarization, P is K over R hat. Well, then that's the polarization. What would the dipole moments at different places be? Well, the dipole moment is P over the volume. And so this is kind of tricky, because what I'm going to do is to put a bunch of points in here. Let's say n equals 1,000. And, you know, I could calculate the total volume of this whole thing. And this doesn't quite work, okay? But then I could say P is just going to be the total polarization, P, divided by the total volume. See, but it'd be the volume per thing, so it'd have to be dV. I think I'd divide that by dV. I'm not 100% sure on this. I'm going to show you one point, though. And so dV would be the total volume divided by N. I don't know that's going to work. But then we can still make our dipole moments like this. And then we can calculate the electric field at any location, wherever we go, just by calculating the electric field due to all those. Well, let's just do it, right? No better way to make a mistake than to just start making mistakes. Okay, so here I am in WebVPython. I am going to give you the code. Let's put a couple things in here. I'm going to call k as 1 and k as 1. I know that's dumb, but capital K is the 1 over 4 pi epsilon naught, and little k is the k in the problem. And now I need to make my sphere. I'm going to make my sphere. I need to pick the values for A and B. So A is going to be equal to, or say B is going to be equal to 1, and A is going to be 0.75 times B. Okay. And then I want N equals 1,000. Let's start with 100. Okay, so how do I make these points in a shell? And I'm going to use a trick. We're going to use random numbers. So let's just do this. I'm going to have a counter of lowercase n. And then what I want to do is to say while n is less than n, I'm going to make it 100 points. So I'm going to generate random values. RT equals, I like this, call this R. So let's say R is equal to B also. Okay, so this is going to be equal to R times vector 2 times random minus 1. So random gives you a number between between 0 and 1. If I multiply it by 2, I get 0 and 2. Subtract 1, I get between -1 and 1. Multiply by R, and I have my space. And then I need to do the same thing for the x, for the y. 2 times random minus 1. 2 times random minus 1. Okay, now let's just put a sphere there. Sphere position equals RT. Radius is going to be, let's say, R over 80. I'm just picking some value. And then let's increase our value of n. N equals n plus 1, so we don't have an infinite loop. So that's 100 points in a cube, though. Okay, so now how do I get that in a sphere? Well, what I do is say I only want to include this if the mag of RT is less than R. Then make a sphere, then count the point. And now it's in a sphere. Maybe it doesn't look like it, but it is. So, and if I change this to 1,000, it makes it a little bit more clear. So that's sphere. I need to now make a shell. So what I want to do is not just say, I'm going to say if this is less than B and mag RT is greater than A, then make a sphere. Okay, so now that's a shell, right? So if I come inside, you can see there's nothing on the inside, and we're looking around. So that did indeed work. But I don't really care about just drawing the spheres. I want to add them to a list so I can use them. So let's make this list of PPs. I don't know why I called it that. So I'm going to add this to the list. PPs equals PPs plus a sphere. Now the other thing I want to do, I don't actually need to draw these, but I'm gonna keep them in there. I also want to include in the property of the sphere the dipole moment. So let's make a property called P, and it's gonna go up here. Let's do this actually first. V is gonna be 4/3 times pi times B cubed minus A cubed. That's the volume of my whole thing. And then dV is going to be V over N. So my polarization is going to be K, lowercase k, times norm RT. Right, so that's good. Oh, you got to spell it right though. Norm RT is oh, you can't even see anything. So norm RT is the unit vector in the direction of that location. So now it's pointing away. And then I need to divide by mag of RT. But I also need to divide by dV. So let's put this as dV times. Okay, so now I have these polarization vectors. Whenever I go back to these points, I can get that polarization vector. So let's just run this. Just make sure it runs. Oh, how about this? Let's make our, let's put some arrows in here. So I'm going to call this thing, what did I use before? Okay, so let's make some arrows at those points so we can see what these dipole moments look like. So let's call this P scale equals 1. I don't know how big they're going to be, but now I'm going to go through all my things. So for PS in PPS, it's going to go through my list of values, and I'm going to take those values and draw an arrow each one. So I'm just going to say arrow. The position is going to be ps.pos. The axis is going to be P scale times ps.p, which is the dipole moment. And then the color is going to be color equals color dot yellow. Let's see if that works. Too big. Okay. So let's make this P scale 0.01. Let's try it then. Too big. 0.001. Getting there. What did I do before? Because it seems like, oh, R is 1. PS. Oh, K times norm RT, mag RT, got that. I had P scales 0.05. Oh, I did this. I did 0.05, and then I just did, I don't really care about the, oh, I do care about the magnitude. Okay, so let's just put this at 0.001. Let's try that. Okay, there you go. There's your dipole moments. Let's make that a little bit bigger. This is a little bit of the art part. Twice as big. Okay, there you go. Now what I want to do is just to calculate the electric field at any particular location due to all of these dipoles. right? I don't have to worry about the surface charge. That's all taken into account with the dipole moments. So if I do that, let's define a function, def ED ROT. So this is going to take some location and it's going to return the electric field due to all of those things. So I'm going to say E temp is equal to vector 0, 0, 0, because I need to add up the electric fields to all the dipoles. So I need to add them to something, and that's what my something is. Now for PP and PPS, I need to calculate, let's call it RR is going to be ROT minus PP.POS. That's the vector from that particular charge dipole to the location. And now I can calculate the temporary, and it's going to add it on there. It's going to be plus 3 times capital K, which is 1, so it's not a big deal, times the dot product of P, which is PP.P, and our norm, RR, and then I need to multiply that by our norm, RR. Okay, well, let's see. So 3 is 3 times all of that. That's fine. Oh, the K should technically be times everything. So K times parentheses minus PP.P. You can't see that. PP.P divided by mag RR cubed. And then I'm going to return ET. Let's just test it. Let's just put RO is going to be vector 1.5 times R00, 0, and print ED RO. Let's just see if it works. Okay, I don't know if that number means anything, but it seems like it works. So what I want to do now is to plot the magnitude of the electric field, or the x component of electric field, as it go from x equals 0 to x equals, let's say, 2r. And I want to show that if I'm in the center part or out of the center part, the electric field's close to 0. It won't be exactly 0. So let's just make a graph. G1 equals graph. Title, let's just put x title equals x. Y title equals EX. Width equals 400. Height equals 200. And then F1 equals G curve. Color equals color dot blue. Now DR is going to be, let's say, R over 100. I'm just going to pick R over 100. Now what I want to do is to say RO equals vector 0, 0, 0. And then while RO dot X is less than, let's say, 2 times R. So I'm going to go twice the radius, even though I probably don't even need to go that big. So that all I'm going to do is calculate the electric field and plot it. I can do that in one fell swoop. F1 dot plot the position, RO dot X, and then the electric field, which is going to be ED RO dot X. I want the X component of the electric field. And then I'm going to move my X value, so RO equals RO plus vector DR00, 0, and that should work. Should. Did I even save this? Let's save this. E due to polarized shell, because you're going to want this, right? You're going to want this code. I'm going to give it to you. Okay, now let's run it. So here you see that we go, and when we get to 0.75, a little bit, this is 0, so that's inside of the big shell, and this is outside, we get 0. Now inside, this shows a problem with polarization. You can't really calculate the electric field inside of there, because as you move through, you're going to get super close to these polarized dipoles, and you're going to get exploding electric fields. So that's why this is kind of jagged. If I run it again, it may look a little bit better because it's random. It just depends on, that looks bad. Let's run it again. I probably hit a dipole. That looks bad. But we're still getting 0 in and out because we're not hitting any things out there. Inside and outside of that material, the electric field works fine. Let's just increase the value, the number of points to 2,000, because if you can do 1,000, you can do 2,000. Ooh, look at that. That looks a little bit better, okay? It should be dying down this way, and still it shouldn't be that big. But I think my calculation of the dipole moment per thing isn't quite right. But we still get the most important thing, that inside, outside, electric field 0. In the actual material, it's a little wonky. Code down below. I'll talk to you later.